Right, so welcome to this class. For those who do not know me, my name is Tutor Post Solutions, and I'm from Discrete Learning Institute. So Discrete Learning Institute simply offers supplementary lessons to whatever you guys will be doing in class. Okay, so that is mathematics, both 1120 and 1110. It is 1100. Yeah, 1100 for those doing NS. For those who are humanities, that's 1110. Physics, there's 1010, 1011. Chemistry, there's 1010 and 1000, right? Okay. And then there's also biology. I think now it's just one biology for all of you guys, but in the past it was divided. So it's biology, 1400, right? So Discrete Learning Institute simply offers supplementary lessons to that. So we get tutorial sheet, we get past papers, and teach you guys exam forecast concept. So that when you go to the tests, to the exams, or when you are answering assignments, you do not struggle. Okay, because we show you exactly what you have to know. Okay, because the way lecturers teach, they will just uh, come to class and then they will just start giving out information, right? They won't even tell you that okay, this one should pay much attention to this and pay much attention to that. They'll just bring the things. So we offer supplementary lessons to all NA students. So feel free to join us. Okay, we have a fully functional website and a mobile application that has a lot of videos that can help you with your studies. Okay, so we have tutorial sheets solved there. We have past papers. We have topic lessons. There's everything that you need in order to have a smooth academic journey in your first year. All right, so today we'll be discussing questions from Chemistry Tutorial Sheet 1. And these questions are basically on the introductory concepts in chemistry. Okay, so we're going to look at questions on significant figures, questions on converting units. Okay, we're going to look at questions on accuracy, precision, and the type of errors that affect the accuracy and the precision. Uh, this question number 5 is also just unit conversions there. Look at the atoms and the subatomic particles like the protons, electrons, neutrons. Okay, we're going to discuss all this in a very simple way that's such that all of you guys actually understand. Okay, we'll also talk about the isotopes. So how can we calculate the average atomic mass of isotope? I know you have a background of knowing isotopes from your senior secondary school. Okay, so these are the questions that we'll be discussing today. And I just hope you guys will be free enough. So if I explain anything and you do not understand, please feel free to ask. Okay, just unmute yourself and then you ask the question so that you learn. Okay, so that you learn. So just take me as your friend, as your brother. Okay, I'm not the lecturer, so don't be afraid to ask questions. So if I explain anything you do not understand, please feel free to ask. Okay, so let's start with question 1 there. Okay, so question 1 says evaluate each of the following and write the answer to the appropriate number of significant figures. So meaning this question here, the first one, is actually on what? Significant figures. Okay, so before we even answer this question, we need to know the rules that govern significant figures. Okay, so first of all, you need to know how to count the significant figures. Okay, so if you are given any number, for example, how do you know which digits are significant, which digits are not significant? So we have to know the rules. Okay, so I'll go over the rules. So the first one is that all non-zero digits are what? Are significant. Okay, so as long as a number is not zero, then that number is going to be what? Significant. So e.g., 55. This 5 and this 5 will be significant. 27. 2 and 7 is going to be what? Significant. Or 5 is going to be significant. So as long as a number is not a zero, then we're going to count it as significant. Okay. And then the other rules, they all talk about zeros. So there are 3 types of zeros. We have what we call as the leading zeros. We have the in-between zeros, or we call them as the captive zeros. And then we have the trading zeros. Okay, so what are the rules that govern those things? So I'll start with the leading zeros. Okay, so leading zeros simply means the zeros that are in front of a non-zero number. So if, for example, I wrote 0.00 and then 5. So you've seen these zeros here. They are in front of a non-zero digit, which is 5 here. So we'll call these zeros as leading zeros. So the leading zeros are never significant. Okay? The leading zeros are never significant. So whenever you have a leading zero, you do not count it as a significant number. So if they ask you how many significant figures are here, we're just going to say 1, which is just this non-zero digit 5. Okay? The second rule about the zeros is the captive zeros. Okay, so captive zeros, or we call them as the in-between zeros. So for example, I have 2, 0, and then 5. Okay, so we see that this 0 here is between two non-zero digits like that. So we call that as a captive zero or an in-between zero. So captive zeros or in-between zeros are always significant. Okay, so if we were to count the number of significant figures here, we'd say they are 1, 2, and then 3. Okay, so we count the zero as significant. Then the other rule is on the trading zeros. Okay, so the trading zeros, these are simply zeros, okay, that come after a non-zero digit. So if I, for example, I wrote 4,000 like this. So you've seen these zeros here. They are coming after a non-zero digit. Okay, so the trading zeros are in two parts. The way I've written this number like that, and then I'm also going to write it like this, and then with a decimal point like that. Okay, so trading zeros are only significant if in that number you have a decimal point. Okay, trading zeros are only significant if in that number you have a what? You have a decimal point. So meaning if I was asked how many significant figures are here, okay, these are trading zeros and I cannot see any decimal point here. So I'm just going to say here there's one significant figure. Okay, but if I go to the other one and then they ask me how many significant figures are here, I'm going to say, okay, here they are trading zeros quite all right, but there's this decimal point there. So I'm going to count all the zeros as significant. So it will be 1, 2, 3, 4. So this one has 4 significant figures like that. Okay, so that's about the trading zero. So it can also be in this form, right? Maybe 2.0000. So as long as there's a decimal point and then trading zeros are part of that number, we're going to count the trading zeros as what? As significant. Okay, it can also be 2, 5, 0, and then point, 5, and then 0, 0. Okay, so this is an in-between zero because it's between, so it's significant. These ones are trading zeros, okay, but they come after a decimal point, or in this number, there's a presence of a decimal point. So we're going to consider all of them here as significant. So how many significant figures are in this number? We're going to say 1, 2, 3, 4, 5, 6, 7. So there are 7 significant figures in this number. Okay, so those are the rules that are going to be helping us determine how many significant figures we have in a certain number. Okay, so any questions up to this point of just discussing the rules? Anybody who has a question before we proceed? Okay, so silence means there is no question. So I'll move on now and talk about the rules that we follow when we are adding two numbers or we are subtracting two numbers that have different number of significant figures. Okay, so I'll say here subtraction or addition of significant figures. Okay, so let's say I have two numbers. Okay, 2.05 and then plus 7.1. Okay, and then I want to add these numbers. Okay, so how will my final answer look like? So if I just get these same exact numbers, just punch them on your calculator, 7 plus 0.1, I'm going to get 9.15. Okay, so now pay attention to the answer. So is the answer correct there? Okay, so the answer according to the rules, when you're adding uh, different numbers with a different number of decimal points, okay, we're going to say this answer here is actually wrong. Okay, so whenever you are adding or subtracting two numbers that have different number of decimal places, your answer should always have the same number of decimal places as the number that had the least of those numbers that you're adding. So you can see here, it had how many decimal places here? It had 1, 2. Then this one had 1. So this one has 2 decimal places. This one here has 1 decimal place. So it means the answer after I add these two numbers should also have 1 decimal place. So it means to correct this answer now, we're going to round it off from there. Okay, so this is 5. If I round it off to the 1 there, I'll just get 9.2. So the correct answer is 9.2. Okay, so this looks simple here, but when you go to the test and then you write your answer as 1.15, they will remove some marks. Okay, they won't give you the full marks because you're not following the rules. Okay, so whenever you are adding or subtracting two numbers that have different number of decimal places, your answer should always have the same number of decimal places as the number that had the what? The least. Okay, so that's the rule when you are adding or when you're subtracting. What about if I'm multiplying? Okay, if I'm multiplying or I am dividing, what is the rule? Okay, so when you're dividing or multiplying, the rule is that the answer should have the same number of significant figures as the number that had the least number of significant figures. So if, for example, I have 7 multiplied by 2.001, okay? So the first number there, 7, only has one significant figure. And then this one has 1, 2, 3, 4. So it has 4 significant figures. So why are we counting these zeros here? Because they are captive zeros. Okay, so meaning that when you multiply this, let me multiply on my calculator. You can also do it on your own. So 7 multiplied by 2.001, that gives me 14.007. Okay, but the rule says that when you multiply or you divide two numbers, the answer should have the same number of significant figures as the number that had the least. So it means here I have to round this off to have one significant figures because this one here had just 1, this one had 4. So the answer should follow the one with the smallest okay, number of significant figure. So here I'm going to round this off from there. So the answer there will just be 10 without any point there, so that the number of significant figure there is just 1. Okay, so those are the rules that we're going to be following when you're multiplying or when you're what? You're dividing. So notice that students usually get confused here. Notice that when you are multiplying and dividing, you are talking about the number of significant figures. Okay? Number of significant figures. When you are adding or when you're subtracting, you're talking about the number of decimal places. So take note of that, okay? And let it sink in your head. Addition, subtraction, number of decimal places. Multiplying or dividing, number of significant figures. Okay, and I've taught you how to count the number of significant figures in any number that you can be given. All right, so now that we know the rules, we can now actually answer this question very comfortably. Okay, so the question says evaluate each of the following and write the answer to the appropriate number of significant figures. Okay, so the first one, A, we have 212.2 plus 26.1 plus 402.09. Okay, so we want to add this thing here. Okay, so here at the university, you don't struggle because you'll be given a calculator to add. That is in chemistry, in physics, or in biology. But in math, no calculator. Okay, no calculator. Unless those who are taking 11, 20, when you start doing probability, which is the last topic. Okay, so for the whole year, you won't be using any calculator. So, but for chemistry, physics, biology, you'll be allowed. So you just get your calculator here. That's the reason why they were telling you to buy calculators. So you just get these numbers, punch them on the calculator, and then see what you're going to get. So let me do that. You should also be doing this on your own calculator so that you confirm whatever I'm finding, right? So 212.2 plus 26.7 plus 402.09. The answer that I get there is 4. In fact, it's 64. So 640.09. 0.99. So this is what I get as my answer. So now remember the rule when we are adding things that have different number of decimal places, right? So when I look at the first one here, it has one decimal place. When I look at this one, it has one decimal place. Then when I look at this one, it has two decimal places. So meaning my answer should have how many decimal places? One, because that is the one that has the least, right? So this will just be equals to. So I'll try to round it off from here. But what do I get when I round it off from there? Okay, so this 9 is greater than 5. So I'll add the 1 to the 9. But when I add the 1 to the 9, it becomes 10. And I can't write 10 here. So I'll get the 1 and push it, okay, to the ones. So this one will go and add to this 0. So it will just become 1. So that will be 60. It will be 6, 4. And then this one becomes a 1 because a 1 is coming from this 9 that has become a 10. So that is 1 and then point. There I'll just remain with a 0. Okay, so this one here will be the correct answer. Why is it correct? Because it has one decimal place, just like this one and this one there. Okay, so any questions there, guys? Any questions that you have? It's clear? Okay,
Yes, it's clear.
all right. Okay, so let's continue now. So now let's look at part B. So part B, it looks to be having a lot of numbers, but you just have to follow some simple rules. So I have 1.646 multiplied by 10 to the power 3, okay, minus 2.18 multiplied by 10 to the power 2, okay, and then plus. So now notice that there are square brackets. So there's a square bracket there, and then inside the square brackets, I have 11.36 multiplied by 10 to the power 4 multiplied by 5.17 multiplied by 10 to the power minus 2, and then another square bracket. Okay, so here now you remember what you are doing in secondary school when you have different operations in one mathematical concept. You are saying we use what? Board mass. I don't know if you guys remember board mass. Okay, so that was brackets of division, multiplication, addition, and subtraction. So it means here for us to find the answer, we first start with what is in the brackets. So which bracket are we considering first? We're considering the what? The square brackets, these ones here. So I want to deal with whatever is inside here, and then we proceed with the other ones. Okay, so here I have 11.636 multiplied by 10 to the power 4 multiplied by 5.17 times 10 to the power minus 2. Okay, so there I can actually remove this to my brackets here and just write this as 11.36 multiplied by, and then I bring this one closer, 5.17 multiplied by 10 to the power 4 multiplied by 10 to the power minus 2. Okay, so I'm allowed to shift the position of this because multiplication in general is commutative. Okay, you will later learn in math when you are learning about binary operations what commutative really means. It just means the order does not matter. Okay, if I say 5 times 2, I'll get 10. If I say 2 times 5, I'll still get 10. Okay, so the order of what you're starting with does not matter. So multiplication has that property. So no wonder I was able to shift these things here. So now here to simplify your answer, I'm just going to multiply this with this. Okay, so I get my calculator. 11.36 multiplied by 5.17. I'll get 58.73112 multiplied by, and then here I have 10 power 4, 10 power minus 2. Okay, so meaning that the bases there are the same because this 10 and this 10 are bases because they have two more powers like that. So I can just say write the base once, and then since we are multiplying this, I can add the powers. So 4 plus minus 2, that's the same as 4 minus 2 to just be 2. Okay, and then now I consider the number of significant figures. So this one here, this number, how many significant figures does it have? It has 4 significant figures. What about this one? It has 3 significant figures. So since we are multiplying, our answer should have the same number of significant figures as the one that had the what? The least. Okay, so meaning I have to round off this number to 3 significant figures. So I'll round it off from here. Okay, so this 3 is less than 5, so I add nothing to the 7. So it will be 8.7 times 10 to the power what? 2. Okay, so that is what I get there. That's what I get there. So I have in this first brackets 1.646 multiplied by 10 to the power 3, okay, minus 2.18 multiplied by 10 to the power 2, and then plus, because there's a plus here, and then whatever was in the brackets here, it has reduced to this. So plus 8.7 times 10 to the power 2. So you see that this topic, okay, it's the foundation of whatever you're going to be doing, okay, going forward. Because in whatever topic that you are going to, then there will be calculations. And those calculations, those numbers will be having different number of significant figures. So you always have to go back to the first topic saying, okay, the numbers that I was given here were this and this. So when I multiply them, I should be able to express them to the correct number of significant figures. So this one is a foundation topic. So everything that you're going to be doing, it will be based on this because you just be doing calculations. So both chemistry, both physics require the same understanding that we are doing here. All right, so here I have this and this and this. Okay, I want to add and subtract them. So this is 1.646 times 10 to the power 3. So you can just try to punch that on the calculator. Okay, or in an easy way, even without a calculator, you can just say, okay, this is 10 power 3. So meaning power 3, meaning this point is going to be moved 3 times going to the right. Okay, if I multiply by 10 to the power 3. But if you do not have that understanding, you can just simply punch on your calculator 1.646 times 10 to the power 3 is going to give you, this point is going to move 1, 2, 3 times. So it would now be there. So I'll have 1,648. Okay, so you can move the decimal point, okay, or you can do it direct from the calculator. And then I'll say minus. Okay, I'll say minus here. Here, what do I have now? Okay, so here I have 10 to the power 2. So I can move this decimal place 1, 2 times because it's power 2. Or I can just punch direct this into the calculator. So it's just going to give me 218. And then plus this one again, we do the same. So I move this point here 1, 2. Okay, because there's 10 to the power 2. Or punch this direct into the calculator. It's going to give you 5,870. Okay, so the number that we have now is that this one has how many significant figures? You can see 4 significant figures. Okay, this one, how many significant figures does it have? It has 3 significant figures. And then this one, how many significant? It also has 3 significant figures. Okay, but our interest here, since we are adding and subtracting, is actually on the number of decimal places. So we see that we do not have any decimal places there, right? So meaning that the number, okay, that I'm going to get as my answer should have no decimal place. And then if I express it as a certain digit times 10 to the power something, that's when it can have a decimal place. And then I'll consider the number of decimal places that I have there. Okay. All right, so let's do this calculation now. So I have 1,646 minus 218 minus, is that plus 5,870? So when I do that, I get 7,298. Okay, but remember, the questions were 10 to the power something, 10 to the power something. So they were in scientific notation. Okay, so you have to make sure that even your answer follows the same consistency. So meaning we can take this back to scientific notation. Okay, so the way the number is written here, it means the decimal place is at the end. So I want to make this number here to be in scientific notation. So what is scientific notation? It's just a number which is between a number which is greater than 1 but less than 10 being multiplied by 10 to the power something. So if the point is there, I want to move it to 1, 2, and then 3 times. So it will go there. So I have 7.2 498 multiplied by 10 to the power. How many steps did I make? 1, 2, 3. So I made 3 steps like that. Okay, and then now since I was adding and subtracting, I can go back and check the number of decimal places that these numbers had. So this one had 3, this one had 2, and this one had how many decimal places? 1. So it means my final answer should only have 1 decimal place. So I'm going to round off from there. So this 9 rounds off to this 2. So it will add a 1 to this. So the final answer will be 7.3 times 10 to the power 3 like that. So that's the final answer that we get there. Okay, so any questions there?
Okay, why didn't we input power negative 3? Because we are moving from right to left. Why didn't we put power negative 3?
Uh-huh. So it's actually the opposite. So when you are moving to the left, like the way we moved here, then the power on the 10 should be positive. And then when you are moving to the right like that, the power on the 10 should be negative. So it's the opposite of what you are thinking.
All right.
Have you gotten it?
Yeah.
Yes. So if we move the decimal point to the left, it means the power will be a positive one. If we move the decimal point to the right, it means the power will be a negative one. So it's the opposite of what happens or what it sounds like. So if you're moving to the left, you expect it to be negative, right? But no, the actual correct thing there is that the power should be positive. If you're moving to the right, you expect the power to be positive, but no, the correct thing is that it will be negative. Okay? All right, so that is our final answer there. And then let's look at part C. Okay, so part C, we have 1912 multiplied by, in the brackets I have 0.0077 multiplied by 10 to the power 4, then multiplied by 3.12 multiplied by 10 to the power minus 3. Okay, and then I'm dividing all this by 4.180 multiplied by 10 to the power minus 4, and then this whole thing here is raised to power 3. Okay, so where do we start from there now? Okay, so where do we start from there? Okay, so we can start with the top part. Okay, so the top part, there's just multiplication there. So it means we can change the order of the numbers on how they are arranged. So I can say on top, I'm going to have 192 multiplied by 0.0077 multiplied by 3.12, and then multiplied by, I now put the 10 to the power somethings. So 10 to the power 4, 10 to the power minus 3 like that. And then down here, notice that it is 4.18 times 10 to the power minus 4. And then this whole thing here is also raised to another power there. So I'm going to distribute this power to everything that I can see inside there. Okay? So this power goes to this 4.13. So it becomes 4.13, 18, sorry, to the power 3. And then multiplied by 10 to the power minus 4, and then this whole thing to the power what? To the power 3. Okay, so that is what we have. So now on top there, what do we get? So you just go to your calculator, simply multiply this with this with this. So it will be 1912 multiplied by 0.0077 multiplied by 3, okay, point, 0.12. Okay, so what do I get? I get 5.93388 according to my calculator. Okay. Then now here 10 and 10 are the same base. So I'll just add the powers there. So it will be times 10 and then 4 plus minus 3. It's the same as 4 minus 3 to just be 1. Okay, so on top, what do I have? Okay, so on top there, I'm just going to have 45.933888 times 10 to the power 1. Okay, I'm done with the top part. What about down here? Down here, I have a 4.18 to the power 3 first of all. Okay, so meaning that if I get this to the power 3, I'm going to have 73.0346 and then 2, and then 32 multiplied by This is 10 to the power minus 4, and then there's a power outside. So I can multiply this power with the minus 4. So this will just be 10 to the power what? Minus 12. Okay, so this is what I now have. Okay, this is now what I now have. Okay, so now I'm just going to express this in the correct number of significant figures. So when I look at the top part here, I'm multiplying, right? So meaning the answer should have the same number of significant figures as the number that had the least number of significant figures, right? Okay. So if I multiply this, this one here has 4 significant figures. This one here has how many significant figures? Anyone? How many significant figures are here?
2.
2. Okay, 2 significant figures, correct. Then this one here has 3 significant figures like that. So it means the final answer that I get from multiplying these should have 2 significant figures. So I'm just going to run this from there. So 9 is greater than 5, so I add the 1 to the 5. So what I have there is 46 multiplied by 10 to the power 1 divided by, and then down there, okay, it was just this number raised to power 3. It was not multiplying with anything. So I just keep the same number that I have. Okay, so now when you reach there, okay, you can do this in 2 ways. If you want a faster method, just punch these things the way they are directly into the calculator, okay? But if you want a long one, you can try to divide them and then do a separate calculation. So just say 46 times 10 to the power 1, okay? Make sure you put them in brackets on your calculator. If you don't put brackets, you're going to find something wrong. And then you say divided by 73.034632 times 10 to the power minus 12 on your calculator. Okay, and then we'll see what we're going to find. So let me do it. You also do it. So 46 multiplied by 10 to the power 1, which is just the same as 10 anyway, divided by, down there I have 73.034632 times 10 to the power minus 12. So make sure you put them in brackets, and then I say equals. Okay, so what I'm getting here is, let me write it down here, 6.2983818842 multiplied by 10 to the power minus 12. Okay, so this is, in fact, it's a power positive 12, not minus 12. Okay, so this is the answer that I get direct from the calculator. Okay, so now we consider the number of significant figures. So this one had 2 significant figures, and then this one here had 1, 2, 3, 4, 5, 6, 7, 8. So we get the number of significant figures for the one that had the least. So it means this number, I want it to have 2 significant figures, right? So I'll round it off from there. Okay, so meaning my final answer was going to be what here? Let's see. So my final answer is going to be, if I round off this 9 to the 2, my final answer will just be 6.3 times 10 to the power 12. So that is the answer there. Correct to the required significant number, the required number of significant figures. Okay, so we are done with this question here. I hope you guys have understood how to do the questions on addition, subtraction, multiplication, and division of these things that have a different number of significant figures or different number of decimal points. Okay, so any questions there? Okay, if there are no questions, let's move and talk about unit conversions now. Okay, so this question here is on unit conversions. Okay, so the question is comparing. So they are asking you which one is greater, and then they give you 2 measurements that have 2 different units. Okay, so you can't compare things that are that have different units. Okay, you have to change them to the same unit. So, for example, for the first one, I have micrograms. Okay, and then on the other one, I have milligrams. So it's either you change this microgram to milligram, and then now you compare, or you can change the milligram to the microgram, and then now you compare, or you can change the microgram to the gram and the milligram to the gram and then compare. Okay, so The bottom line is that when you're comparing two measurements, they should have the same units. If they don't have the same units, then you cannot compare them. You cannot know that, okay, this one is the bigger one, this one is the smaller one. No. So now when it comes to unit conversions, okay, there are a lot of methods that you can use to actually convert units. We have the method where you use the conversion factors, okay, but that one is only convenient if you actually know the conversion factors, okay. And then we have the one where we use dimensional analysis. Okay. I'll send videos in the group for this, for whatever I'm mentioning. So we have the one where we use dimensional analysis to convert. And then we have the one, which I believe is the simplest one, where you use the metric system table. So the metric system table is this thing that you can see here, this guy here. That's the metric system table. Okay. So the metric system, what is it? Okay, it's just a table that contains prefixes that have a symbol, and attached to that symbol is going to be a certain number or a certain value or a certain magnitude. So I'm sure most of you go to Facebook, right? So on those Facebook posts, you will see that on that like button, there will be something like maybe 1K. Okay. And for those big people, you see, if you go maybe to a Facebook page of Ronaldo or Messi, you see 1M. So these things, Makea and these M's are what we are calling as prefixes. So they have a meaning to them. They are not just there for decorations. Okay. So we have different prefixes. So like the K here, it means kilo. Okay, so when you just see 1K, it means kilo. And a value that is attached to the K is 10 to the power 3, or simply 1,000 like this. Okay, so when you see 1K, it means that post had 1,000 likes on it. If you see 1M, the M has a value of 10 to the power 6, which is just the same as 1 million. Okay, so it means that video, that post, or whatever that thing has 1 million reactions to it. That's what it means. So that's the same metric system that we are talking about. So you know, I know you know the K. You've known it now because I know you go to Facebook. You've known the M, that it's 10 to the power 6. Now you have to educate yourself and know all these others that you can see here. Okay, so the smallest, uh, for the ones that you're going to use, there are other smaller ones, but for the ones that you're going to be using, you guys, you start with the pico, nano, micro, milli, centi, deci, and then deca, hecto, kilo, mega, giga, tera. Okay, so you have to know the value of the prefixes. So if they say giga, it's the same as 10 to the power 9 there. Okay, if they say tera, it's the same as 10 to the power 12. If they say mega, that's the median. It's the same as 10 to the power 6. Kilo is 10 to the power 3. Okay, hecto is 10 to the power 2. So as long as you know this table, then unit conversions will never be a problem to you. Okay, for those units where you're just changing from one factor of the units to the other, you'll just be solving it very easily. So for example, before we start solving these ones, right? For example, if I have 5 kilometers, I want to convert these 5 kilometers, okay, to centimeters. So how easily can I convert these using the metric system table? I'm just going to say, okay, 5 multiplied by, what is the value of the kilo? Okay, so the value of the kilo we said is 10 to the power 3. Then I'll say divided by, so I'm converting from the kilometers to the centimeters, right? So divided by the value of this C here, which is the centi. So according to the metric system table, the centi is 10 to the power what? Minus 2. So I'll divide with 10 to the power minus 2 like that. Okay, so you multiply with the prefix where you are from, because this is 10 kilo. So I'm from the kilo. And then you divide by the prefix where you are going, which is the cent. Okay, so meaning if I had 5 centimeters, changing it to kilometers, then my conversion would be in such a way that I say 5 multiplied by 10, what the value of the centi? It's minus 2. And then divided by where I'm going, which is the kilo. So it would be 10 to the power what? 3. So that's the easiest way in which you can convert these units. Okay, and then here you just say 5 multiplied by, and then you combine these. because this here is just the same as 10 to the power 3 over 10 to the power minus 2. So I haven't changed anything here. I can say this is over 1. If I multiply 5, multiply by this, I still get back this. 1 multiplied by this, I still get back this. So this will just be 5 multiplied by, and then these ones are dividing, they have the same base, so I subtract their powers, right? So it will be 10, and then 3 minus 3, 2. So it will just be 10 multiplied by 5 multiplied by 10 to the power 3, and then minus and negative there. They will make a positive. So that will be to the power 5 like that. So converting the 5 kilometers to centimeters, it will be the same as 5 times 10 to the power 5 centimeters like that. Okay, so that's how you can easily convert using the metric system. So just replace wherever you're coming from, replace it with its value, and then divide by the value of the prefix where you are going. Okay, so that's what we're going to use to convert A and B. So on A and B, they've said we have 3,245 micrograms. Okay, and then the other number there is 0.00515 milligrams. So we can't compare like this because they have different units. So what we need to do is convert one of them to the other. Okay, so let's convert the micrograms. We convert it to the milligrams. Okay, so meaning that I'll just get this same number. So 3,245 multiplied by, what's the value of the micro? So this symbol here, it's like a U, but it's not a U. It's actually called mu. Okay. So the mu represents the micro, and it has a value of 10 to the power minus 6. Okay. So I'll just multiply by 10 to the power minus 6, and then divide it by the value of the prefix where I'm going, which is the midi. So midi has 10 to the power minus 3 like this. So this part is the same as 3,245 multiplied by 10. Okay, multiplied by 10 to the power minus 6 over 10 to the power minus 3. So this will just give me 3, 2, 4, 5 multiplied by, I just write 110. And then since these are dividing, I subtract the bases, the powers. So it will be minus 6 minus, okay, so this minus is because they are dividing. And then what is the other power? It's minus 3. So I have minus 6 plus 3, which will just be minus 3. So this will be minus 3 like that. Okay, so this is what I get, and I was changing from the micro to the milli. So this is now milligram. Okay, so 10 to the power minus 3 is just the same as 3,245, or you can just do it direct on your calculator, multiplied by 1 over 10 to the power 3. And 10 to the power 3 is the same as 1,000. So I'm dividing this thing by 1,000. So what do I get? So 3,245 divided by 1,000. I'm going to get 3.245 milligrams. Okay, so now I can compare because I have the same units. Okay, so I'm just going to say this guy here is the same as 3.245 milligrams. So between the 3.45 milligrams and this is 0 point something something milligrams, which one is greater? Okay, we see that the greater one is this one. So you see how simple it is now to compare if you change them to the same units, right? Okay, so this one is greater. So in your answer, you're not going to say this one is greater. No, you state it explicitly in the way that it was given. So you're going to say the greater one, okay, the greater one is 3,245 micrograms like that. So it's the greater one. Because when I change it to the milligrams, it's actually greater than the other one. Okay, but you're also free because not all of you are going to use the same method. So someone else can choose to convert the milligrams to the micro. Okay, convert the milligrams to the micro. They'll still end up at the same conclusion. All right, so if there are no questions, I'll move to part B. So part B, what do we have there? So part B, we have 3,257 milligrams or 0.000475 kgs. So we just want to convert, okay, one of them to the other. So let's convert the kgs to the milligram. Okay, so I get this number 0.000475 475. Remember it had kg, so I multiply by the prefix value for the k, which is kilo. So that is 10 to the power 3. And then I divide by where I'm going, which is the milli. So milli is 10 to the power minus 3. Okay, so what do we notice here? Okay, we notice that we're 10 to the power 3 and then 10 to the power minus 3. So this will be the same as 0.0000475 multiplied by, and then this one will just be 10, and then I can subtract the powers. So it will be 3 minus, because these things are dividing, and then minus 3, which is there. So this will just be 3 plus 3. And this will just be 6. So this will be 6 like that. Okay, so I'm multiplying this whole number here by 10 to the power 6. So meaning that I'm just moving this point 6 times to the what? To the right, because the power there is actually positive. Okay, so I can say 1, 2, 3, 4, 5, 6. So the number that I'm going to get there now, if I move it 6 times, or if I multiply by 10 to the power 6 direct on the calculator, I'm going to get 4, 7, 5, and this will just be what? Milligrams. Okay, so now which one is bigger? Okay, between this one that we've converted to milligrams and it has given us 475 milligrams, and this guy, we see that this guy is bigger. So we're going to say the greater one is 3257 milligram. This one is the one which is greater. All right, so that's how we can simply do that. So any questions there, guys? Okay, we'll move to C. So C, those are volume conversions, so we have to know some specific conversion factors there for us to work out that one. Okay, so we can't use the metric system directly here. So there they're saying they have 981 cubic centimeters, and then on the other side they have 0.25 liters. So we just have to change these to liters or these to cubic centimeters. So let's change everything to the liters. Okay, so what is the conversion factor of the volume changes? So what you have to know is that 1 milliliter is the same as 1 cubic centimeter. Okay, 1 milliliter is the same as 1 cubic centimeter, and 1 liter is equals to 1000 milliliters. Okay, 1 liter is equals to 1000 milliliters. Okay, so having this conversion here now, we can use it to convert this guy into liters. So we're going to use a bit of dimensional analysis. So I'll say 981 cubic centimeters divided by 1. So remember, I want this thing to disappear so that I have my liters, right? So I'll say multiplied by, and then I'll get the conversion factor that has the cubic centimeter, and I'll place it in such a way that the cubic centimeter should cancel. So I'll say 1 cubic centimeters is equivalent to 1 milliliter. So here it will mean this and this is going to cancel, and I'm just going to remain with the milliliters. Okay, but before we cancel, let's multiply again by another conversion factor which we put there. So this one here says 1000 milliliters is the same as 1 liter. So notice that I'm actually placing this in a strategic way so that whatever I don't want should cancel out. So this milliliter is on top here. No wonder I'm putting the milliliter down. If it was down here, I would have put this 1000 milliliter on top there. Okay, so I want this guy to cancel with that, and then the milliliter to cancel with that, so that I just have the liter, which is the desired what unit. So it will be 981 multiplied by 1 liter. I just get 981 liter divided by 1000. Okay, so this will just give me what now? Okay, so this one will just give me 0.981 liter. Okay, so between the 0.25 liters and the 0.981 liter, which one is bigger? Okay, so we see that the bigger one is going to be this guy here. So in your answering, you don't mention the one that you actually converted. You mention the one that was initially there. So you're going to say the greater one is 981 cubic what? Centimeters, like that. Okay, so any questions there? Okay, let's look at the D. Okay, let's look at D. So D, we have 105 uh, degrees Celsius and 373 K. Okay, so we're going to say, let's convert one of them to the other. So I know the formula for converting the temperature to the kelvins is just the temperature in degrees. Okay, so I'll say temperature in degrees here, Celsius plus 273. Okay, so I have 105 plus 273. So what do you think I'm going to get as my temperature in kelvins? It will be 378 kelvins. Okay, so this one here is equivalent to 378 kelvins. And then here I have 373 kelvins. So which one is bigger? This guy is bigger. So in my answer, I'm going to say the 105 degrees Celsius is actually what? Greater. Okay, as simple as that. Okay, so that's how you can simply answer those questions. So any questions there? We'll move to the next part. Okay, so if there are no questions, let's move to the next part. All right, so now let's look at this question here, which is a very nice question because it tests your understanding, okay, and your reasoning as you'll be going to the lab to do these experiments and the like. So how are you going to be reading the readings on those burettes that you'll be using, the conical flask, the measuring cylinders and the like? How are you going to be reading? Okay, so it also emphasizes about the different precisions that the measuring instruments can have based on the calibrations that it has. Okay, so let's do this one. So they're saying the beakers shown below have different precisions. Okay, so this one beaker will say, okay, let this beaker A, this one be beaker B, and then this one be beaker C, like that. So the first question here, they're saying label the amount of water in each of the three beakers to the correct number of significant figures. Okay, label the amount of water in each of the three beakers to the correct number of significant figures. So now the way we record measurement is that the value that we're going to record will always have two parts. There will be the certain part that you know, okay, for sure you know that, okay, this is correct. And then there will be the uncertain part. So the uncertain part, okay, is the one that is going to help us have the correct number of what? Significant figures. Okay, so when I look at this beaker here, there was a measurement that was there, and then they've just zoomed in, okay, on where the water is actually ending on this beaker. So you can notice that the measurements that the way they calibrated this first beaker here is that it's increasing in ones, right? So this is 26, and then it goes to 27, and then it goes to 28. So it's increasing by what? 1 milliliter. Okay, so it's increasing by 1 milliliter like that. So meaning that the marks are marked 1 milliliter apart. So from the 26, go to 27, and then we go to 28. And then where can we see the water level there? So the water level is above the 26, okay, and it's almost halfway. Okay, we can see it's almost halfway between the 26 and the 27. So now the 26, I'll write it here, is going to be our certain value. We are certain that actually this water reaches 26, right? And then now between this 26 and 27, we are not certain. So we are going to get the uncertain part of the number. Okay, we're going to get the uncertain part of the number. So the uncertainty, we are going to estimate it to the nearest 0.1 milliliter. Because here the difference is just 1 milliliter, okay? The uncertain digit is going to be uh, to the nearest 0.1, okay? Because these ones is 1 milliliter apart, right? So the uncertain digit is going to be this same number, but with a 0 point in front. So 0.1 milliliter like that. Okay, so meaning that somewhere halfway there, okay, we can say halfway between the 26 and the 27, we'll end up with something like a 0.5. 0.5 like that. And then this will be the final reading, milliliters. So you can see that the number that I have, it has this part, we call this as the certain. And then this 0.5, we're going to call it as the uncertain because we are not sure of it. Okay, we are just looking at the beaker and then determining the reading. Okay, all right, so that's the reading for the first one. Another one can say 26.4, still reasonable enough. They still mark you. Okay, and then when I look at this beaker B here, when they zoomed in the reading there, okay, you can see there's 20, 30, and then 40. So it's increasing in what? 10 milliliters. Okay, from the 20, 30, and then the 40. And then this water level here, we can see it's past the 20. So 20 is actually very certain. Okay, 20 is actually very certain. And then now, as I move above here, I can see that the water level there is actually above the halfway because it's more closer to the 30 than to the 20, right? Okay, so it might be somewhere 28, 27. Okay, because we're just estimating and that value are calling it uncertain because we're not very sure of it. So I'm going to say, okay, since the the difference in calibration of this beaker is in 10 milliliters, then the uncertainty should be 1 milliliter. Okay, so it simply says that the calibration that you have, just divide it by 10 to get the uncertainty. Here we had 1. So if you divide 1 by 10, you get the uncertainty, which is 0.1. Here I have 10. To get the uncertainty, I'll just divide this 10 by 10. Okay, I get 1 milliliter like that. Okay, so somewhere there, it should be, somewhere 28 to 27, right? So we are not sure of that unit. So I'm just going to write there 27 milliliters like that. I'll take here as it is 27. Okay, so that will be the reading for this one. If I go here, check the calibration that we have there. Okay, so these calibrations are increasing in 0.1 because from 26.4, I go to 26.5 and then 26.6. So they're increasing to with the 0.1. So what is the uncertainty there? I'm just going to divide this with a 10. So I get 0.01. Okay, so I'm very certain that 26.4 has been reached. And then there's this part now that is above this thing here. Okay, so it's just slightly above the 26.4. So I can evaluate it as as a point 002. Okay, this is a point 002 there because I'm looking at the uncertainty there. So I'm just going to add a 2 there. Someone else might add a 1 or a 3, it will still be reasonably correct because the value that we're getting is uncertain, okay? But the uncertain part, we all should be correct. So the uncertain part is this one here. This 2 is uncertain. The certain part here is the 2. The 7 is uncertain. Here, the certain part is the 26, and then the 0.5 is uncertain. Okay, so those are the rough measurements that I can see from the beaker. Okay, but as you will notice when you go to the labs and be doing this, each and every one of you is going to have a slightly different measurement that they are going to actually write because someone here might interpret this as 26.41. Okay, and then you say 0.42. It will still be correct like that. Okay, so the reading here we've said it's 26.42 milliliters. Okay, if the units that they are using is milliliters anyway. This one here, we're going to say 27 milliliters. Then this one here, we're going to say 26.5 milliliters. So we have expressed all of them there to the correct number of what? Significant figures. Okay, so that was the first part. Then part B, they're saying, is it possible for each of the 3 beakers to contain the exact same amount of water? Okay, so the answer here is that yes, they can actually contain the exact same amount of water. Okay, if no, why? Okay, so this one is not a possibility because they can actually contain the same amount of water. If yes, did you report the volumes as the same in part A? Explain. Okay, so if yes, did we record the volume as the same? The answer is no. We didn't record the volume as the same because you can see the precision here actually differs. This one is 0.1, this one is 1, and then this one is 0.001. So the precision here, or the uncertainty here, is actually 0.1. Here it's 1. And then here it's what? 0.01. Okay, so we did not record the volume as the same. You can see this has 1 decimal place, this has 0, this one has 2 decimal places. Okay, but is it possible that all the beakers have the same water? Yes, they have the same amount of water, but because of the way the beakers are calibrated, we can't get the same measurements from all of them. We're going to get slightly different, but you can see that all these measurements are actually just very close to each other. Okay, so that's the explanation you can give there. And then on part C, they're saying suppose you pour the water from these 3 beakers into one container. What would be the volume in the container reported to the correct number of significant figures? So they just want us to add the volumes there. So I have 26.5 plus 27, okay? And then plus 26.42. So what did we say was the rule when you are adding these things? This one here has 3 significant figures. This one here has 1. I'm not considering the number of significant figures, sorry. Considering the number of decimal places because I'm adding. So this one has 1 decimal place. This one has 0 decimal places. This one has 2 decimal places. So it means my final answer should follow the one with the least, which is just 0 decimal places. So let me add these things now. So I have 26.5 plus 27 plus 26.42. So I'm going to get 79.92, but it says the list should have 0 significant figures. So I'll round off from there. I'm just going to get 80 like that. Okay, so that will be the final answer there. So any questions there? Any questions that you might have?
So is it going to be in centimeters or in meters?
Yeah, so here if they didn't give the units, okay, so you can use any units that are used for the volume. So here I was using milliliters, milliliters, milliliters. So I can also say milliliter here, but they actually didn't give the units. Okay, is that okay?
Yes.
Okay. Okay, so let's move to the next question now. So the next question is on what we call as accuracy and precision. Okay, so these are very simple concepts that that you guys should use to actually get the maximum marks in your assessments or in your assignments and quizzes and the like. Okay, so before we even do the questions here, okay, we have to explain what is accuracy and what is what? What is precision? Okay, so I'll start with accuracy. What is accuracy? Okay, so accuracy is how close your measurements, okay, or the results of your measurements are to the true value. Okay, so how close measurements are to the true value, to the true value. Okay, so how close the measurements are to the true value, that's what we call as accuracy. So let's say I'm measuring the weight of this stone. So let's say this is the stone here. And then the true weight of the stone is maybe 5.5 grams. Okay, so I get this stone now, I put it on the measuring balance. So because I'm measuring this on the measuring balance, we always have some degree of uncertainty. So you cannot find the exact weight of that thing. So maybe I measure and then I find um 5.49. Okay, I measure again, maybe I find 5.48 gram. I measure again, I find 5.989 gram. Okay, so you can see that the measurements here that I'm getting are actually very close to the 5.5, right? So we'll call these measurements here as accurate because they are very close to the true value. Okay, right. So when you're considering accuracy, if it's just one measurement that you've made, you can compare it directly to the true value like that, like the way I'm doing here. I can compare this to this, and then I say, okay, this is accurate because it's very close to the true value. But there are some times where you have a lot of values that have been measured, and then you want to state if those measurements are actually closer to the true value. So you don't compare them individually, like you get this one, compare it this one, compare it this compare it into this. No, you always have to find the average of them and then compare that average value to the true value. Okay, so here I would say 5.49 plus 5.48 plus 5.989. Okay, and then I divide by how many they are. There were 3. Okay, I'm going to get 5.653. And then now you compare this measurement here that you've gotten the average to this. And then now you can state if it's accurate or it's not accurate. Okay, so that one should be done whenever you have more than 2 measurements. And then you want to state something about the accuracy. All right, so the other thing now that we have to compare is, that we have to learn is the precision. Okay, so what is precision? Okay, so precision is how close the measured measurements that you've made are to each other and not necessarily to the true value. So the true value can be 5.5 grams like we did. And then you, when you're measuring, maybe you find 2.5 grams. Okay, again, 2.45 grams. And then 2.51 gram. Okay, so you can see that the true value is 5.5, but when I'm measuring these things, I'm finding values that are not close to it. Okay, but these values that I'm actually finding, they are close to each other. So how close the repeated measurements are to each other is what we call as the precision, and not necessarily close to the what? To the true value. Okay, so meaning that some certain measurements are going to be precise, but they are not accurate. Okay, they're going to be precise, but they're not accurate because their average is not even close to the true value. But when you look at them, they'll be close to each other. So we'll say that they are precise, but they're not accurate. Okay, so that's the difference between the accuracy and the precision. Okay, so another thing that I have to explain is the 2 errors that affect accuracy and precision. Okay, so there are 2 errors that you have to take note of. They are what we call as random errors. Okay, and then there are what we call as systematic errors. So what are random errors and what are systematic errors? Okay, so random errors are errors that happened randomly and they vary and they go both directions. So if my true measurements is 5.5, right? And then I'm measuring this stone, and then my measurements are experiencing random error, then you'd expect measurements to be in this way. I can have 2.5 grams, okay? And then I say 4.9 grams, and then I have 7.1 grams, and then maybe 8.9 grams. So you see that in my measurements here, I have numbers that are greater than the true value and also numbers that are less than the true value. So whenever you see such a thing, if among your measurements you have some that are greater than the true value and some that are less than the true value, then just know that those measurements are affected by the random errors because the random errors are happening anyhow. Okay, they are going above the true value, they're going below the true value. So they're happening anyhow. So if you have such a situation, just know that, okay, these measurements are actually affected by random errors. Okay, and then systematic error, this is an error that happens in one direction. So meaning that all the measurements that you measure are either all below the true value or they are all above the true value. So if I get this 5.5 gram, I measure it, and then maybe I find 3.7 gram, 4.4 gram. Okay, I find another 4.9 gram as my measurements. You see that all these measurements that I've had, they're actually less than the true value. So we're going to say the error that is affecting this is systematic error. Okay, or it can be another situation where all the measurements that you have are actually above the 5.5. So you're getting 7.1, 7.9, 8.1. Okay, you can see that all of them are actually above the true value. So we're going to say that is systematic error because it's happening in one direction. Okay, it's either they are all above or they are all below. All right, so now that we've known that, we can now go back to this question and answer it confidently. Okay, so let's do that. So we're going to say, the question says what anyway? To determine the volume of sodium hydroxide, 3 students, Cleopatra, Joshua, and Eugene, actually, yeah, okay, made a set of measurements with the burette from 3 trial titrations in the table below. So this is one of the labs that you are going to do in chemistry. It's called titration. Okay, so we have trial 1, trial 2, trial 3, and then we have the different names of these students here. Okay, so there's Cleopatra, Joshua, Eugene, and there's also Natasha here. So I don't know why here they said 3. So there should be 4 here, then they should add Natasha here. Okay, so part A, if the true volume needed to complete the reaction is 15.62 centimeters, okay, which of the students illustrate the following? Okay, so the true value we've been given. The true value is 15.62 centimeters. Okay, and then which students illustrate the following? So first of all, let's talk about the accuracy and the precision of each of these students. So for the first one, okay, who is Cleopatra here? We can see we have 17.2 something, 17.2 something. So these ones are actually precise, okay, because the measurements are close to each other. So they are precise, but are they accurate? Okay, we can't know. We have to take the average of this and then compare it to the true value. So on your calculator, you put 17.23 plus 17.21 plus 17.26, then you divide by 3. So I'm going to get my average for Cleopatra. It will be 17.23. So now, is this 17.23 closer to this 15.62? The answer is no. Okay, so for the first student here, who is Cleopatra, it will be precise but not accurate. Okay, what about the second one, who is Joshua? So when I look at the measurements there, there's 18, 17, and then 15. So these measurements are not close to each other, so they are not precise. Okay, they're not precise. And if something is not precise, then it can never be accurate. Okay, it can never be accurate because it means the measurements are just going all over. So here we're also going to conclude that not accurate. Okay, immediately something is not precise, then it cannot be accurate. Okay, what about Eugene? Eugene, it's 15.6 something, all of them. So we're going to say they are precise. Okay, but are they accurate? Let's find the average. So it will be 15.64 plus 15.61 plus 15.63. Then I divide by 3. So the answer that I'm getting is 15.62 6666. So I just round it off to 2 decimal places. I get 15.63 like that. So you ask yourself now, is this thing closer to the true value? We see that yes, it's closer. So we're going to say for Eugene, it's precise and it's also what? Accurate. Okay, what about Natasha? Natasha, they are all 16 point somethings, so they are precise, but are they accurate? We can't tell. We need to find the average of this and then compare it to this. Okay, so I get 16.61 plus 31 plus 16.37 plus 16.34, and then I divide by 3. So that one is just going to give me 16.34. So 16.34, is it close to the 15? No. So we're going to say this one's not accurate. Okay, so once we do that, it means this question is even done. Okay, so now let's just follow whatever they were asking us. So which of the following students illustrate imprecise, which means not precise and not accurate? Not precise, not accurate. That is what? Joshua. Okay, and then precise but not accurate. Precise, not accurate, we have 2. We have Cleopatra, okay, and Natasha. All right, and then precise and accurate data is this guy, Eugene. Okay, so Eugene is very precise. So when you go to the lab, be a Eugene, right? Be very precise, be very accurate with whatever you'll be doing there. All right, and then B, they're saying give a reason, give a possible explanation as to why data can be imprecise or inaccurate. Okay, so why can data be imprecise? Okay, so data can be imprecise because of the random errors. So random errors affect precision. Okay, so now we have to give specific examples here. How do these random errors come about? Okay, so they can be due to paradox errors. Okay, so when you are reading the meniscus of different uh, measuring instruments like the beaker, the measuring cylinder in the lab, okay, you can read the meniscus in a wrong way, okay, or reading it differently from time to time. So parallax errors are going to cause random errors, okay, just because of how you are seeing or how you're getting the measurements. Maybe you see 12.2, your friends sees 12.4. So those are parallax errors. Okay, another reason for imprecision or random errors is what we call as inconsistency, okay, or inconsistent endpoint judging. Okay, so like in this lab here for titration, you are going to be adding a base to an acid or an acid to a base. So as you are adding the base to the acid or the other way around, okay, if you are inconsistent at the end point where you stop adding the other reagent to the other one, okay, you're going to get inconsistent results because sometimes you'll be overshooting, meaning you've poured a lot of acid, okay, than you are supposed to, or you've poured a lot of base than you are supposed to what? To pour there. So it's consistent in the end point, which can cause to overshooting or undershooting. And then the air bubbles, okay, in the beakers. That's why when you go there, they always have to uh, tell you to actually remove the air bubbles in the, not the bigger, but in the burette. Okay, air bubbles in the burette. So before you add anything there, you will be told to remove the air bubbles so that your experiments are actually correct. Okay, and the other reason is that no sweating. Okay, so sweating is simply mixing whatever you've put maybe in a conical flask. So you are just shaking the conical flask in a circular manner. So you are swirling. So not enough swinging for whatever is there to actually mix completely can be a cause of the random errors. So this one, we consider it under poor techniques. Okay, under poor techniques like that. Okay, um, what other reasons can make data now to be inaccurate? So inaccurate, we are talking about the systematic errors now. Okay, we're talking about the systematic errors. So what causes the systematic errors? Remember, these are errors just in one direction. Okay, so we're going to say the zero error. Okay, so your instrument, if you've not zeroed it, okay, it can measure something that is actually bigger than whatever you are measuring. Okay, the other thing is instruments that are not calibrated. Okay, it's not calibrated correctly, you're just guessing. That can be the reason for the systematic. And then also, like in the experiment for titration, if you're using wrong concentrations of the solutions that you're supposed to use, okay, it can cause systematic errors. Okay, some other reason is contaminated solutions. Okay, so it's not just an acid, maybe they added some things there, okay, and you don't know that it's actually contaminated. It's going to give you wrong results. Okay, and then yeah, so those are some of the examples and the reasons why the data can be imprecise or inaccurate. So any questions there, guys? Okay, so if there are no questions, let's look at the last one there. Okay, so the last one, I believe I've already answered it. It said, what is wrong with saying a set of measurements is imprecise but accurate. Okay, so we said anything that is not precise, okay, as long as it's not precise, then it can never be accurate. Because by not being precise, it means the readings are actually far away from each other. And the readings that are far away from each other, even if you get the average, you not get a value that is closer to the what? To the true value. Okay, so a set that is very scattered, which we are calling imprecise, gives a large uncertainty. So you can't confidently claim that the measurements are close to the true value. Okay, so immediately you just hear not precise, then it can never be accurate. Okay, so the problem there is without precision, you can't demonstrate the accuracy. Okay, you can't demonstrate the accuracy. All right. Okay. So any questions, guys? Any questions there?
Yes,
You said you had the question?
no.
Oh, okay. All right, so let's move and talk about the next question now here. Okay, so here, this question, we need to understand it. Okay, we need to understand it very well. Okay, so the question says, a non-SI unit of mass used in pharmaceutical work is the grain, GR, okay? And they've given us the conversion factor here. They're saying 15 grain is equivalent to 1.0 grams. An aspirin tablet, okay, contains 5.0 grain of aspirin. Okay, an aspirin tablet contains 5.0 grains of aspirin. So meaning one tablet, okay, has how many grains? 5.0 grains. Okay, now a 155 lb arthritic individual. So this lb simply means pounds. So this is just the mass, but in the units of pounds. So a 155 pounds, okay, arthritic individual takes 2 aspirin tablets per day. Okay, so one day they take 2 tablets of what? Aspirin. All right, and then there we've also been given the conversion factor from the pounds to the kgs. So the first question there, they're saying, what is the quantity of aspirin in 2 tablets? Okay, expressed in milligrams. Okay, so if one tablet has 5.0 grain, what about 2 tablets? Okay, so 2 tablets, I'll say x here, just cross multiply. So x will just be equals to 10. Okay, grain. So 2 tablets have 10 grain, but they want us to express this quantity in milligrams. Okay, so I'll go back to this conversion factor. It says 15 grains is the same as 1.0 grams. So now I have 10 grains. What will be the mass in grams first of all? So x cross multiply, 15x is equals to 10. I divide by 15, I divide by 15, I'll get x is equals to 10 divided by 15. Okay, so 10 divided by 16, I get 0.6666. The 6 continue to go. Okay, so I can just round it off to 7, and this will be grams. Okay, so this is the quantity in grams, but remember here they said we should express it in milligrams. Okay, we should express it in what? In milligrams. Okay, so I just have to know the conversion factor now for converting from the grams to the what? To the milligrams. So 1 gram is equivalent to 10 to the power 3 milligrams. Okay, or 1 gram is equivalent to 1,000 milligrams. So I'm just going to say now I have 0.66667 grams. Okay, what will be my mass in milligrams? So cross multiply 1 multiplied by this, I get x is equals to, this is 0.666 multiplied by 10 to the power 3. I just move this decimal place 1, 2, 3 times. Okay, 1, 2, 3 times. So I have 666.7 grams. Oh, milligrams, sorry. Okay, so that is the quantity of the aspirin in 2 tablets expressed in what? Milligrams. So 666.7 milligrams, like that. Okay, so now this quantity here is taken per day because they said this person takes 2 aspirin tablets per day. So per day, this person will take 666.7 milligrams. All right, and then part 2 or part B, they're saying what is the dosage rate of aspirin expressed in milligrams of aspirin per kilogram of body mass? Okay, so they said milligrams of aspirin per kilogram. Okay, so meaning the dosage formula, okay, the dosage formula just from the units, it will just be the quantity, which is in milligrams, we already found it, divided by the mass of that individual. And it should be in kgs. So the quantity is already in milligrams there. So it means I just have to change this mass here. That was in pounds. So 155. Okay, I just have to change the mass that was in pounds there. LB, I have to change this to kilograms. So the conversion factor we are given here, saying 1 LB is equals to 0.454 kgs. What about if I have 155 LB? What mass am I going to have? Okay, so cross multiply, x multiplied by 1, that will be x is equals to, and then this guy multiplied by this. Okay, what are we going to have? So 155 multiplied by 0.454. So I'm going to get 70.06 kgs. Okay, so the mass of that individual in kgs is this. The quantity, I already have it. So the quantity is 666.7 milligrams. And then the mass is 70.06 kgs. So I divide this. So 666.7 divided by, so also do it on your calculator, divided by 70.00. Okay, I'm going to get 9.52. Okay, 4, 2, and then 9, and this will just be milligrams per kg. Okay, so to what number of decimal places am I going to express it to, or to what number of significant figures? This one has 4, this one has 4. So I'll round it off to 4. So it will just be 9.52 4. This will be milligrams per kg. Okay, so that will be the dosage there. That will be the dosage there. Round it off to 4 significant figures because I'm dividing. Okay, so now we want to answer part C, this one here. Okay, I want to answer part C, this one. So part C, what are they saying? They're saying, I can erase these other things now. They're saying at the given rate, okay, at the given rate of consumption of aspirin tablets, how many days would it take to consume 1 kilogram of aspirin? So remember, this person per day, okay, he consumes this amount of aspirin. So I'll say 1 day, this guy consumes 666.7 milligrams. What if I have 1 kg of aspirin? So it means I have to change this 1 kg to the what? To the milligrams. Okay, so I'll say 1.0 times the k there is the same as 10 to the power 3. And then I divide by where I'm going, the mid, which is 10 to the power minus 3. So this will just be 1 multiplied by 10. And then this will be 3. And because I'm dividing this to be minus and then minus 3, so that will just be 6. So to the power 6. So it's 1.0 times 10 to the power 6 milligrams. Okay, so this will be x. So cross multiply now here. So it will be 666.7 x is equals to 1.0 times 10 to the power 6. Okay, and then I divide this by 666.7. I divide that by 666.7. So x will be equals to, I just punch this now onto the calculator. Okay, So 10 to the power 6 divided by 666.7. Okay, I get, according to my calculator, 1.5 times 10 to the power 3. And this will be the number of days. Okay, so for them, or for this person to actually consume a 1 kg of aspirin, it will take 1.5 times 10 to the power 3 days. Okay, so any questions there, guys? Any questions that you have? Okay, so I think if there are no questions, I'll end here for now. Okay, but I'll post the videos for all the solutions there. Okay, I'll post the videos for all the questions in the solution. All right, so have a blessed night.
Thank you.